My name's Adrian Kerr, Temperzone's R&D manager. Today's talk we're going to run through some key drivers, which are key trends which are driving our R&D program at Temperzone, and then we're going to go through one of the new range of products that we're about to put to market, heat pump water heaters, and finally a few sort of case studies showing how we have applied and what the impact of application of these products has been. So firstly, I've been told to talk louder, so if it's too loud, say if it's not loud enough, say that too, please. Looking at energy use in buildings, looking at in the non-residential space, around 16% of our electricity goes in commercial applications, which a third is for lighting, about a third is used for HVAC, and a fair bit of our national gas consumption, around 10% of our electricity is used to heat water. And over the past 15, 20 years, what we've seen is a significant change from having water sourced systems, water as an energy carrier in buildings, to having refrigerant as the energy carrier in buildings, which we see with the VRF style systems and the popularity of those systems. If you look at how much energy the commercial buildings use, it's around 4 times that of a residential building. So looking at the sort of key trends which are driving the industry, the first is the move from a fixed rating point for air conditioning products to a seasonal energy efficiency rating. And this test method basically requires us to test our units at a number of different test conditions under different loads, which is where we get the part load efficiency from. And it very much drives us towards having variable capacity products. So variable speed fans, variable speed compressors, electron expansion valves to adjust to the variable refrigerant mass flow going through the systems. The technology being used to do this is significantly more complicated than the electronics, but you get much better energy efficiency from doing so. And just a quick sort of, for those who don't follow the regulatory side, so this old Energy Star rating label is being replaced next year, 1st of April, with this zoned energy rating label. And part of the zoning, as you'll see, the performance of different products has been rated to different climates. And that climate is based on this bin profile. So this is the bin profile for our market, New Zealand. And I've got the traditional rating points, the Tier 1 H1 rating test point, and you can see how much of the year the units actually operate in part load relative to those points. The vertical scale, for those who can't see, is the number of hours and each temperature each unit, and the ambient temperature sort of burns along the bottom. And when you look at the impact of part load on system efficiency, it's not just that the compressor is more efficient as it works more slowly. It's also that the load on the compressor is much less too. So you can sort of do, this isn't a standard, but if you approximate the speed a compressor needs to run at to meet a given heat load, and you look at the efficiency, the effect that has on efficiency, you can see that in cooling, when it's a really hot day, the compressor has to run flat out. Your efficiency is relatively low. And as the conditions become more mild, and as the compressor slows down, because the conditions are more mild, you get a very significant increase in the efficiency of these systems. Exactly the same, but in converse with cooling. For convenience or such, I've swapped the capacity scale around the other way, so this time it's low capacity to high capacity. As it gets increasingly colder, the efficiency becomes lower. So you can see that most of the time a variable speed system operates in these very mild conditions, not at all where the rating points, which are here and here, so it very much drives us towards doing variable capacity systems. The other key driver is the phase down of HFC refrigerants by the Kigali Amendment. This is a global process that started this year. New Zealand ratified the agreement last week, and for implementation on the 1st of January next year. The aim of this program is to reduce 0.5 degree global temperature levels by 2100. If you look at the refrigeration industry as a whole, so we're talking vehicles, we're talking air conditioning, you're talking farm to plate, cold chain refrigeration. In 2016, they estimated that 486 tonnes of HFCs was lost to the environment and New Zealand each year, equivalent to 1.1 million tonnes of CO2. It's the equivalent of 540,000 vehicle cars of emissions each year. Or to put it another way, each kilogram of refrigerant lost to the air is the emissions of one car for 1 car. This is based on R410A, a refrigerant like 404 or 407C. This is roughly twice that. So we've got here, it's not the nicest graph, but it's looking at HFC imports into New Zealand. This is for the start of the emission trading scheme and company stockpiled, which is why those are big reduction next year. But anyway, and this is the Kigali Amendment phase down, and this is New Zealand's phase down path. This drop here basically means that we're coming out of R410A into a lower GWP refrigerant, and then we come out of those late 2020s to a zero GWP refrigerant. And if you look at why we chose R32, so residential products have gone to R32 largely already, and we're just starting the process of converting commercial products. As you go to the left on this graph here, units have to become bigger per kilowatt of cooling that you deliver. And as you go to the right, they become smaller and more compact. And as you go up here, you get increasing GWP, and the line in the middle separates flammable ones and explosive ones, and toxic ones from ones which are non-ones. So we've taken R410 and R32 is exactly, it's 50% of R410A. It's got a GWP of 675 versus 2000 for R410A. It's mildly flammable. It's not explosive. It's a difference between a poof and a kaboom in terms of when it goes bang. It's a refrigerant which does not sustain burning if you remove the source of ignition. So you can have a stream of it, you can light it, it's a very weak, soft flame, you remove the source of ignition, it instantly extinguishes. It's the biggest change as an industry is you can't, regulations won't let us pump the stuff around buildings in vast quantities. So there's regulations, how many grams is quite high, but it's not enough to run federal-left style systems. It's more efficient, and we find that with a new products we can achieve between a 75 to 80% reduction in GWP per kilowatt of cooling by making this change at a higher SEER. And we get excellent heating performance too. In quite cold climates, particularly if you're trying to drive to quite high temperatures, you need vapor injection. A vapor injection has a third port, a second suction port on a compressor. It allows you to put an internal refrigerant economizer, that's well done, on the liquid line. That allows you to get more capacity and more COP when it gets cold. And the second function is it allows you to run liquid injection, which is when the discharge temperature gets too hot, you can start bleeding in liquid refrigerant into the compressor to control the discharge temperatures. And this is where you start to see these sorts of units operating down at -15, -20 degree in heating. It is because of this technology here. And in our whole heat pumps, we're offering this as an option. So Central North Island, usual suspect places, South of Christchurch, inland South Island, particularly if you do high temperature, you need this if you're using R13. So just looking at it more broadly, it's been very much marketed as green. It's not incredibly green, but it's a heck of a lot better than where we've come from. It really is affecting the IF systems, and we see an increased role of hydronics as a consequence of this. The advantage of hydronics is you have a very low charge, and because you're not pumping refrigerant around. So rather than having 100 kilograms to do a 50 kilowatt cooling charge, you might only have 6 kilograms. So not only do we get the GWP reduced by a lot, we can also use much less refrigerant for the same kilowatt cooling by changing the format of air conditioning systems. So in terms of the R&D program in total, as a whole, we've been putting a lot of focus on our inverter product. You'll start seeing next year a whole new class of inverter package rooftop units coming through, as well as other products we're doing. We started work with Honeywell in 2014 on the next generation of refrigerants, adopted hydronic as a strategy in 2015. We adopted a new class of thermoshell, a heat exchanger. A thermoshell, it's a tube and can style heat exchanger. So the water sits in the tube, refrigerant sits in the can. The advantage of it is it separates phases. So any refrigerant which has condensed sits to the bottom. Any refrigerant which hasn't evaporated also stays at the bottom, and it separates them out. So it's a really, really good heat exchanger for this class of product. We developed an IoT development platform to support new products. In 2017, we started R32 field trials this time last year, and we have been doing quite a few field trials over the last few years to push this program through. So I want to focus now on heating systems, because that's the point of today's talk, Temperzone talk. So there's a very strong push that's starting to take place now around transitioning away from a fossil fuel-based economy to a low carbon economy, and it's very clear that one of the ways this is going to happen is through increased electrification of our energy system. But there's multiple standards and regulatory consultations coming through at the moment, preparing the framework for this. I'm going to Melbourne tonight for a water heating standards committee. 2 days there, we're doing the standards for heat pump water heating systems, which is the starting point of our NEPS type framework for these products. The New Zealand Green Building Council and the Zero Carbon Bill of the government are looking towards having no new fossil fuel going into building new buildings around 2024 and have a complete phase out of fossil fuel in existing buildings by 2030. The stationary energy is really the low-hanging fruit with this. It's a relatively easy thing to get rid of fossil fuel out of buildings. And we see refrigeration systems as being one of the most energy efficient ways of doing this. So looking at different ways you can do this, replacing central boiler systems with a distributed heating system. So rather than driving your primary circuit at the highest temperature that your building requires, split that up into potable water, into space heating, and supply those loads separately from the appropriate type of heat pump, rather than having it all in one primary with the exchanges on the secondary side. Reconditioning boilers on water source units. Gas, usually heat pumps can do the same thing. Electric heater banks, you can use heat pumps, boiler coolers. So this is an example here. This is just a AHU fan coil with a inverter and a heat pump system that will provide the same heat for about a quarter of the electricity. Potable water, like we've got here, multiple tanks, simple pass, top-down heat pumps with a separated main system so that you maintain the thermal stratification of the tanks. If you look at the emission intensity on different fuels, you can see electricity, we can reduce that greatly using heat pump technology. And if you're doing new space heating designs, designed to a little bit lower temperature, there's a huge difference between design to 60-65 versus design for 55. You go from a COP of 1.2, 1.3 to a COP of over 3 with a small 5-degree change. So we've come up with a range of heat pump water heaters. They exist in, at the moment, three chassis. There's a 200 kilowatt one that we're developing at the moment. And they're called, of all things, a single fan chassis, a twin fan chassis, well, imagination is exemplary, and a quad fan chassis. But each of these products come in different variations. So we configure the components and the logic in each one of these units for the target application of them. The overriding principle is for a given supply water temperature, the colder or the warmer you can make the return water into it, the more efficient the system is. And the entire project is like how you reconfigure both the unit and the application to take advantage of this principle. Very much based on inverter compressor. Compressors were very much trying to drive that part load efficiency. The controls become very simple because all that we're mostly doing is changing the water flow. So instead of directly controlling the inverter like we used to with aircon, we can control the water flow. The compressor sees the change in water flow and what the return water temperature is, and it runs whatever speed it needs to meet the design level water temperature. Where we've got multiple inverters, at the once we move out of the peak efficiency point of each inverter, we switch on another one and another one and another until we have them all going, and then we ramp them all up and do it simultaneously. And then as the load drops, we drop them off so that we are always keeping within the peak performance for each inverter. So looking at water heating itself, so we're talking domestic hot water now, potable hot water. Around 10% of our electricity goes to heat hot water. We achieve with a single pass water heater around a 65% annual energy savings using this technology. We designed our units to comply with the G12 AS2 emission limit controls. We're very much trying to reduce the use of ring mains. But looking at water heating systems, there will often be the need for a ring main, but the more that you can reduce the need of it, it really reduces the total energy consumption, and the units are very much driving around maintaining the thermal stratification. This is where hot water floats on top of cold water. It forms a very stable thermal transition, and by doing that, we can keep cold water entering our units, which is where we get the high efficiency from. So, the pump water heaters are not replacement boilers. You can't design, I need a gas boiler, you're just going to drop in hot water heat pump. Much of the industry does this, and what you see is after 4 or 5 years, the compressor, the top of the compressor will usually be quite discoloured, quite burnt, quite dull. The paint's quite dull, and it's just because the compressor's been operating outside of its envelope. They usually sit there mostly between 50 and 60 degrees C water temperature, and they're not terribly durable if you do that. We need to start designing water heating systems that stay within the compressor envelopes, and that's a compressor which is overstressed. It's not just that it's not efficient, but it's last year. Durability is really important. So when you stick these systems in and they don't last particularly that long, then you don't deliver the payback for customers. Combination systems, this is where you see underfloor and potable, or poles and potable, and all these sorts of combining different heat, different temperatures with one system. And the problem with this is that you are invariably setting your system up to to the highest temperature that you need, but you're degrading the performance of everything else. Now, where the main load is at a higher temperature, there's more sense to it. But very often, there's this space heating and potable water heat combined, and the temperatures will be that of potable heating, water heating, but the amount of potable water that you need is quite low, and the main load is at space heating. Yet, and will be far more efficient and cost effective if you split them into two separate systems. So we've come up with different configurations of each unit. This is the titanium heat exchanger for doing DX into pools. The potable water has a de-superheater. This is the vapor injection. This is the superheater to get the high temperature, and then your underfloor system. This is what you saw downstairs, and then there's another 5 variations of this, where we can have part of this, and one of these spots reverse cycle, and all the rest of it. A lot of the units come with turnkey controls. So this is what the industry is largely doing now. They've got a buffer tank for space heating. It's configured like this. For hot water heating, this pipe is down here. And basically, the unit's heating this tank on a deadband arrangement, and then the hot water is being used for whatever it's being used for. And the approach that we're taking is a unit that's an inline inverter-based heating system, where there's two pipes going straight into the field, and coming back from the field is the coldest possible water, and we require that all the water that's coming back must have passed through a heat exchanger. So we don't use flow bypass valves. We do variable flow based systems rather than fixed flow based systems. And what you get from doing this is much greater efficiency and durability of the systems, and very often they're a lot cheaper to install. Also, what we're trying to do with this is to mainstream this technology as an alternative to gas. So, our potable hot water, we take the cold water in from the bottom, we heat it to 60 degrees in a single step, and we float this hot water on the top down in our tanks. Now, a unit like this will do around 500 litres per hour, so that we can extend that storage by up to 1,000 litres in every 2-hour peak demand period, and around a third of the unit cost is offset by the reduction in storage that you need. So just to run through a few examples. So we looked at a KFC. So these examples illustrate some of the principles that we've been talking about. So we took a KFC store, we monitored one in minutes fixed, and then we put forward a design proposal, and then we got a job in Wollaston to apply this design to it. So we basically, a cave still has a large amount of potable hot water, which they in part use to defrost chicken. So the water is used in about 400 litre batches about 3, 4, 5 times a day, depending how much it's up. And it also has a large fresh air temperature load. And if you don't temper the air, the food goes cold by the counters as it's being made. So we've used the spare capacity of the heat pump to supply the fresh air temper demand to. But and we've used the variable flow concept for this. So we've got a variable speed pump in the unit that maintains a fixed level water temperature of the heat pump, and then we've got a variable speed pump in the fresh air tempering side to maintain a cold return to keep the tank permanently stratified, which is where we get the efficiency from. So on this day, we'll ignore the off up there, but we're taking 10 degree water coming in, 18 degree fresh air tempering, and the units doing the hot water. And we also use inverter based units as opposed to fixed speed in the kitchen dining, and we added a little coil, a little duct for the fish air. So this is what the system looks like. It's a thermally stratified tank. It's got a little tank on top, and the little tank takes a 60 degree water of the main storage tank, heats it between 65 and 68 electrically to meet the commercial kitchen 65 degree water at the tank requirement of the water account. And then we've got a thermally stratified storage system that's also zoned. So we've got a few sensors in this tank, and as the hot water in the tank is drawn down for defrosted chicken, the cold layer rises up through this tank as the hot water comes out the top. And as the cold water layer hits these parts of the tank, the variable speed fish air temperature pump changes how it behaves. So we basically prioritize the supply of hot water to the kitchen at the cost of fish air temperature. So at this point, the heat pump turns on and starts a reheating stage. At this point, the pump goes to minimum speed. Instead of doing 18 degree fish air temperature, we do 13 degree fish air temperature. And at this point here, the pump stops altogether, and the unit would prioritize kitchen hot water. But because we heat the water from the top down, even if you get to this point here, it very quickly recovers. So if you see the data, this is a picture of the tank showing the different parts to it. We do a control box that is plug and play. We basically have half the size of the tank, or we've half the size of the heat pump to meet the load by taking this approach, which has made the heat pump much more cost effective than otherwise. And we've got a monitoring system where we had flow meters and temperature sensors around the system to calculate the energy consumption. And this is a day of use. So you can see the domestic hot water balancing around is fully timed back. This is the top element, the top of the tank. You can see how well thermally stratified this tank is. Each of these spikes here are this boundary layer between cold and hot, passing past a sensor in the tank. And you can see how sharp they are as the temperature changes. So with such definition as it passes past this point. And you can see here how the supply air temperature is being controlled, and when they've drawn off a whole bunch of water to defrost chicken, you can see that the pump's gone to minimum speed, and then for a very short time it's turned off altogether, and then it's gone back to minimum speed, and it's quickly recovered again back to full efficient temperatures. So if you look at the performance of the system, the stored is around 2,200 units a day, and the of which 57 megawatt hours a year was for fresh air tempering. That made half of what the total store requirement of water heating was, and we achieved a 68% reduction in electricity usage. A seasonal SEER in 2024 that was worth about $11,000 at 15 cents per kilowatt hour, and we've reduced the total heating and water heating, fish air tempering and water heating proportion of the store's total energy usage from 23 to 8%, which is the equivalent of 23 electric vehicles driving 50 k's a day each day of the year.
Sorry, what was the case study? Did you say Winton?
With Waterston,
North.
just a bit south of Western. But since this time we've done one in Bombay, Auckland, and Christchurch. Another project is a water replacement project. So this project took a central diesel board that had a primary circuit that went around 4 buildings of a Potable, and we removed the diesel boiler and we did a distributed heat system. So we split off the space heating from the potable water heating. The space heating only operating half the year, around 8 months a year, and the potable hot water obviously goes the whole year round. And there's big tunnels under the buildings where the plant is, and by removing that primary loop, the tunnels went from in the middle of July very, very warm, after the heat loss is coming off, to very stark. And we basically have set up a bunch of these units. So these 2 units here do all the wards of the hospital. It's 180 kilowatts installed capacity. It's an inline system. There's no buffer tanks. The 55-degree water out of these inverter-based units goes directly to a series of radiators and ceiling panels around the wards. These are the domestic hot water systems. And the energy savings from doing this is really huge, because if you're applying the appropriate temperature hot water to the appropriate application, rather than running the entire system to the hottest application of the site. And it really works on this inverter-based part load performance of the systems. And it means that your part of the year when you're not doing space heating, you're not running this huge network that has effectively a very small load on it. And so Potable is $111,000 worth of diesel that's saved. The total diesel energy, the diesel reduction in diesel is 282,000 litres of diesel a year saved between those 2 sites, with around 200 grams of energy, and done environment site, power car, awesome. Now the energy savings here aren't just the heat pumps, it's also, it's as much about the climate distribution. Another project was a coal store in Sydney. The coal fields is a very cold part of Sydney. And it took out a 120 kilowatt free stage electric heat bank and the air handler, and we put in a large waterfall, one of these inverter-based units, and a very simple design. There's no buffer tanks or storage. It's just an inline system. It's got a little PLC that is set up to control temperature and flow rates. It's controlled based on the supply air temperature. So as the heating load increases, the pump goes faster to maintain the supply air. That increases water flow, means more inverters turn on. Each inverter is run at the peak of its efficiency. And so that as an inverter starts to go too quick, another one comes on, and another one, and it drops off the other one, so that the whole time each inverter is sitting at its peak efficiency. Here it is here, very basic, easy to apply system, which happens to save a lot of money in terms of energy over the year. This is done by Coles, their contractor, whose name is escaped me, but they monitored the system over 12 months. Another project was Mount Cook, YHA, but anyone talks to me about the cold weather performance of these units. I punch out this case study. This is a YHA, it's an 80-bed backpackers at Mount Cook. It's we've done a integrated solar thermal. It's the first single pass solar thermal system with a single pass hot water heat pump system that we've ever come across. We think it's the first time it's been done. The advantage, usually solar thermal and heat pumps, they compete. They both want to make cold water hot. So you end up with the solar thermal doing the preheat, and that degrades the performance of the solar thermal. Whereas with this system, we've got them both heated water to 60 degrees when they run, and top-down heating of the tanks. So the cold water in the bottom of the tanks is never preheated by the solar. And then the heat pumps, there's a sensor in this tank. So if the cold water lag goes too high, the heat pump, because there's not much sun that day, the heat pump will come on and just heat from the top of the tank down to keep the top of the tank hot without heating the entire tank. It's a system where there's no supplementary heating. There is gas backup, but it only comes on if the heat pump faults. So it meets the load, all you is a vapor injection without any supplementary heat. The heat pump sits, poor cousin, under the stairs at the back. This is what it looks like. So this is the solar hold-off sensor. So you start the day each day with the tanks full of hot water, and then if this tank here becomes cold, then the heat pump turns on just enough to heat to this point. Otherwise, it's a solar thermal during the day, and around 3 o'clock in the afternoon, the heat pump turns on, and that does whatever the solar hasn't done. Sometimes we don't get much solar gain. and other times we get quite a lot. And this project was a finalist in the Deloitte Energy Awards a few weeks back, saving So, there are sort of a few projects that show this the kind of approach we're taking with the units. If we go back to the HVAC space, usually there's a boilers and a coolant tower, or and we wanted to replace the gas boilers with hot water pumps for doing a 2-pipe, 4-pipe style system. And for our water source systems, we want to start using heat pumps and reverse cycle units that basically water condition rather than get